Welcome to BKW Physics. I'm Mr. McConley, and today we're going to talk about the topic of friction. And I want to start this by you imagining that all of a sudden you wake up one morning and friction has been turned off. Just envision that for a second. Could you slide yourself to the edge of the bed to get up? Well, no, because you keep slipping. There'd be nothing for you to grab onto. Could you walk? No. Well, I don't think so, because most of your walking ability relies on the fact that you have some sort of friction to plant your feet to act as a balancing point. Could you drive? No. Could you write your homework down? No, and that'd be a terribly sad thing. So, lacking friction would be something that most of us can hardly even relate to. Definition-wise, friction is, it's a force. It's a force. And it's a force that opposes motion between two surfaces that are in contact. I tried to highlight or make a different font, the key words in here that you got to pick up on. It's a force that opposes motion between surfaces in contact. The force is parallel to the surface, but it's in the direction that opposes the slipping of the two surfaces. So, an example, if I'm trying to slide a book across the table to your left, then the friction would be to your right. Okay? So whatever direction you're trying to move something, friction is the other way. Static friction. There's two types of friction actually here. And for the people in the classroom, if I'm going a little faster than you can copy it down, we can go back at the end. You can, I can go back to some of the slides. But static friction, it opposes the start of the motion. So when you try to get something moving, say it's something heavy. Have you ever pushed something pretty stout, pretty heavy? And you're like, oh, and you're pushing, and then it goes, and it slides, and then all of a sudden it got a lot easier once it started moving? That you didn't imagine that. It's not like you were wimpy and then all of a sudden got really strong. That's the idea of static friction, because static friction is the friction that opposes the start of the motion, and by the way, it's going to be the larger of the two. Now kinetic friction, the sliding friction, this is once you get it moving. So you have static, it's hard to get going. Once it starts sliding, it turns to kinetic friction, and it also opposes the motion. But it's when two things are already moving relative to one another. So you've already got the thing moving, and now you're just sliding along. I got a question that relates right here. Will a car stop faster by not locking the brakes or by locking the brakes and skidding? And I think you probably know the answer to this, because all cars nowadays, it's standard equipment that they have to have anti-lock brakes. There's got to be some physics behind these things. They don't just randomly make those sort of decisions in the car industry. So, why is it that the anti-lock brakes are making you stop faster?
Maybe so tires don't lock up and it like pulsates the brakes.
It does.
So
when the tires lock up,
it keeps skidding.
You go to sliding friction. Sliding friction is the lesser of the two frictions. It's a lower number. So if you can keep the tires almost sliding and then don't let them slide, almost sliding and don't let them slide, you're really hovering on static friction. And if you can hover on static friction, you can stop quicker. And this is especially true when you get like wet surfaces, like wet leaves, wet ground, snowy surfaces. If you can keep the brakes from sliding, you up the friction, which is a good thing when you're trying to stop. Okay? So that's why we use anti-lock brakes. The force of kinetic friction is less than static friction. That's what I've been trying to say. Just saying it in a lot of different ways. And the second question, is it harder to start something moving or keep it moving? I've also already touched on that. It's harder to get it moving because static, once you get it moving, the number goes down because it turns to kinetic. Now there's an equation. And if you're following the pattern that I normally give notes in, you would put a box around this, because in your reference table. It says FF equals That's actually a mu. It's a Greek letter. It's right after lambda. So lambda, mu. It's a U, and actually, when you write it correctly, there's like two tails on it. So FF, force of friction, equals mu Fn. Now we learned yesterday, what was Fn? Thinking back, was normal force. It's like my book's sitting on the table. The table must be holding my book up. If the table's holding my book up, it's supplying the normal force. The mu, though, we haven't talked at all about yet, and it's called a coefficient of friction. And basically what it is it's a relative, it's a comparative term, a number, it's a coefficient. And if you think of two things that slide easily across one another, like steel on steel, metal on metal slides really easily, it will have a low coefficient number. The mu value will be low. If you think of two things that really stick together strongly, that will have a high coefficient value. Sandpaper on wood. That's going to have a high coefficient. It sticks pretty well. And the reference table actually lists these coefficients of friction. I'll just hold it up here. I'll hold it a little closer to the camera. It's on the front page of your reference table. Whether you can see it or not, it's up for grabs. But it's on the front page. It's on the bottom right-hand corner. And there's coefficients of friction, and it compares some things. Like one of the ones that has a pretty high value is rubber on concrete. Makes sense, since you put rubber tires on cars and they drive across concrete or asphalt. So that's a pretty high number. A low number is like a waxed ski on snow. Concept there, you want to go fast on your skis, so it slides pretty easily, so it's a low coefficient number. And the lowest number you'll find is at the very bottom, and I encourage you to look on your own reference table at some point and notice that the two slipperiest things that they list on the New York State Physics Reference Table are Teflon on Teflon. Teflon is some slippery stuff, and it's an additive that they actually put in oils now, and it's also a coating that they put on fry pans so that you fry your eggs. Eggs don't stick to the bottom of the fry pan because that irritates everybody. So, if you're pushing a textbook across the table, I want to give you a visual representation of what the forces would look like, the motions to the right. Basically, if you're pushing it that way, that's called your applied force. Opposing the motion is your friction force. Now, if it's moving, just moving across the table, is this the force of friction static or force of friction kinetic? Kinetic. This is kinetic because we're moving. And then you have gravity, which is always relentlessly pulling down on you, and the normal force, which Amit noted a minute ago, is the one that kind of holds it up. Okay? So these two are equal and opposite, assuming the book isn't sinking into the table. I don't know why it would be. They kind of cancel each other out. Now, I'm going to go through this kind of quick, and if you're watching the video, you can go back and slow it down, but basically what I do is I say the net force is each of the forces added together. But the force of gravity is equal and opposite to the normal force. So they cancel out, and now you're just left with net force, applied, and friction. That's this line right here. Net force is equal to the applied and the friction. Net force is the same as mass times acceleration. The frictional force, we just learned, is the same as mu times Fn. But remember, Fn is the same as Fg, so we can actually find Fg and plug it in for Fn. That's what we do right here. Now we have this fancy mess of an equation that says the mass times acceleration is the applied force plus mu and mg, because mg got plugged in instead of Fn based on this concept here. So we can plug things in. I didn't give you any numbers on this problem, but we can plug things in and solve for the missing one. I went through that very quickly, but for today, that's physics.